the end of Robot Week, and I don't think we've broken any of the three laws. We managed to get through the week. We've had we dealt with a lot of difficult representation challenges. Um, and Now we're getting ready to wrap this thing up, and we're going to do something a little different this time. And we're going to this talk. We're going to instead of the normal aspect of robot programming, the mainline processing that we have talked about so much of the week. We're going to talk about the challenges that the participants faced for dealing with the robot's perspective in this whole robot programming project. You know, our Thor project, theory of robotics. This talk we're gonna talk a little bit about the robot's perspective and the environment and the kind of programming and considerations that are necessary to achieve a successful robot project. But before I get into the talk, I want to do a few acknowledgments. I want to acknowledge the Rome group at CTEST Laboratories. Those folks are always helpful to us. The cell at CTEST Laboratories as well. They provided most of the hardware and the software that we're using. They supported us with anything that we needed in terms of oscilloscopes or wiring or power supplies, any of that kind of stuff. Rome itself gave us that. Also, our Retro Underground Roboticists, our RUR folks, want to acknowledge their contributions and the many folks that helped us along from that group. And at this time, also, I want to just cite our sources, our old-ass references that we use. Common Sense Reasoning by Eric Mueller. The Behavior-Based Robotics book by Arkin played a big part in a lot of the discussions that we had this week and a lot of the challenges in some of our deep dive. Knowledge, Representation, and Reasoning by Ronald Brockman and Hector Levesque. Also a big part of the programming architectures that we were exploring. And so also our OATs, our old-ass technologies, the hardware platforms that we used most. There were a lot of things involved. Our Rigol oscilloscopes, those were important this week. So I guess we should have shouted out Rigol here. But our Sun T1000 server, the Sunblade 2000 workstations that were used, and the mini Arduinos and Raspberry Pis that were part of this project. So there's acknowledgement. And also, just a shout out to any of our Neo-ACM robotics enthusiasts, or any of the enthusiasts out there from the Oak Hill Robotics Collaborative. And whether you guys are catching this live, or even if you are catching it, in its recorded form, shout out to you folks and everybody that helped and everybody that contributed to make the this year's Robot Week successful. I thank all you guys. And we, like I said, we want to focus this talk here. We won't go too long. I know we're all ready to get out of here for today. It's been a long week. We want to really just do a stop by the robot's perspective. And we want to talk a few minutes here about the robot domain environment, the actual environment the robot is doing the tasks in, and where the robot has to work, where the robot starts, where the robot stops, the kinds of things that it has to manipulate. A lot of times when we're focusing on solving the robot programming problems, the first place is not the first consideration is not the robot environment, and maybe it should be, because without considering where the robot is at, what the conditions are, what kind of objects it has to manipulate, the scenario and situation that the robot is in, it's not likely that our programming efforts are going to be successful. So today we're going to talk mostly about the raw and the SAW view. I'll say a little bit about law at the end. And these acronyms are Robot Accessible Worldview, the Sensor Accessible Worldview, and the Logic Accessible Worldview. And so we're going to talk about these three views, but from the perspective of the actual robot that's being programmed. There's a human perspective here. Obviously, human beings were involved in designing the models for all of these views, but today we really want to just deal with this thing as it's seen through the robot, right? That's the trick that we're getting into. And so some of the minimum considerations that we had for our Thor project this week, some of the challenges that the participants had to deal with, and these are just some minimal. This is a minimum list here. I cannot. We do not have time to enumerate all of the considerations, the robot domain environment considerations that we dealt with this week, and that you always have to deal with when programming robots. This is just a minimal thing for a minimal list of considerations. We have the physical space that the robot is in. The physical, how big are we? Is this an outdoor environment? Are you dealing with an underwater robotic situation? Is it an aerial environment? Are we, talking about miles or meters, kilometers? What that physical space is. All of the geometries that are involved. We'll get a little drill down a little bit into that a little later. What kind of surfaces are we dealing with? We can't make the assumptions that we have a single kind of surface. And so in more than a few robot applications, you have different kinds of surfaces and surface types. The surface might be smooth or frozen or, at various angles. Maybe we have a gravel, grass, dirt, stairs, a lot of different things that you might have to consider in the surface challenges. The environmental conditions, weather, again, extreme heat, radiation situations. Are we dealing with rain, snow, indoors, outdoors? So the environmental conditions have to be taken into account. Those things, like surfaces and the environment, those things will have an interesting interaction with the power usage of the robot. How much extra power is needed, or how much power is reserved. Those things could be influenced both by surface and environmental. Those are the kind of things that you don't think of often in robot programming that plays into the actual algorithms that get involved in the kind of programming that happens. What occupies that physical space of the robot's domain environment? Are we talking about, is it going to be a situation where you have people, animals? Is it just going to be inanimate things? Are the things in motion? Is everything going to be in a single location, or are locations changing? What's the disposition of those things? Do we have situations where the robot may be manipulating things that are could be changing state? Originally starting out with ice and ending up with a situation that because of the environment, the ice is melting. And so, are the dispositions of the living or non-living things dynamic or not dynamic? Are their locations static or not? There's a lot of things to consider when we're looking at just the robot domain environment and the occupants of that environment. What are the safety considerations? Lots of things go there. And a big one here: what is the situation? What is the scenario that the robot is in? Right? So this physical space, the geometries, the surfaces, the environments, those occupants, they all are occurring in some kind of context. Is the robot in a factory context? Is the robot in a shopping mall? Maybe we have a robot Santa and it's Christmas, and that's the situation. And the robot is the goal of the robot is to hear the little kids, what their wish lists are. We have to identify what that situation and the scenario and the events in that scenario and the moments within those events. Those are all considerations when we're looking at the robot's domain environment. And then a lot of times we got into worrying about how we were going to deal with object interaction, or how the robot was going to negotiate or navigate some particular terrain, and that tends to catch most of our attention a lot of times in these robot weeks. But this week we placed a lot more emphasis on the programming for the situation and the scenario, and dealing with representing situations, scenarios, events, and moments within those events. The energy requirements and interactions is also another big focus of our robot's perspective this week. Everything is impacts that the energy requirements here, and those energy interactions, and depending on what the situation and the scenarios are, the expectations of the robot and the robot's expectation of the environment. And let me stop and pause there. That's a thing. We have expectations of the robot, but the robot also has expectations of the scenario and the situation, right? And so those expectations it's a two-way street. A lot of times that's overlooked in the robot programming. And so it's stuff we do here at CTEST Labs in our cell and our roam groups, our H2O groups as well. We are very much concerned with the two-way expectations on the user side and expectations on the robot side. Also, a big part of that robot domain environment are the time scales. What kind of times are we dealing with here? Are we dealing with milliseconds or seconds, hours, days, weeks? What's going on? Is it a continuous time continuum? Are we in some kind of event loop? Are we dealing with linear? Are we dealing with discrete time or continuous time? What units? I say, are we dealing with kilometers or meters, or are we dealing with grams or centigrams? The meters thing is a big deal. The coordinate systems that are involved. We found that out in some shocking, spectacular fashions this week. There are many coordinate systems that are involved in robot programming. Many coordinate systems, and the notion of location, where the robot is, where a thing is, where an individual is within the coordinate space. Can we do everything with Euclidean space, or did we need to do something else in representing these domains? So that robot domain environment, when we say from the robot's perspective, what I mean here is the robot's interaction with its physical space the geometries, the surfaces, the environmental conditions, the occupants, the situations and scenarios, events and moments. What is the robot's interaction with these things? How does it interact? What's the interface? And that interface, we're going to explore that interface through 3 views. We have something called the raw view, the robot accessible worldview, the sensor accessible worldview, and the logic accessible worldview. Now, it's the case that the robot accessible worldview is really a superset, and the sensor accessible worldview is a subset of that, right? And the law worldview is also a subset, but we want to consider those things separately. But let's take, for instance, we have our scenario here. We have a somewhat of a birthday party scenario, and we have what are we talking here? 1, 2, 3, 4, 5 tasks. We only want the robot to do 5 things. We want the robot to light the candles. We want the robot to greet and scan the guests. We want the robot to scan the presents for weapons and explosives. Okay, this is a different kind of birthday party, I see. We want the robot to take out the trash. And this, we have an asterisk here because that might happen multiple times during the party, right? We may have clutter building up at multiple times, at multiple points during the party, and we need the robot to come in and clear some things out. And the last task that we want the robot to do is to reset the party space after the party is over. Okay, now in this scenario, right? We one of the things we did this week, we identified that our scenario, we want to break our scenario down into a number of situations. And we show 6 situations here, but it really goes further than that. We break situations down into events, and then we break events down into moments. But for the purposes of this talk, we'll stop at the situation level. So we have a situation, one situation where Happy Birthday has been sung. In situation Q, we're going to be blowing out the candles, and maybe there's some applause once the candles are blown out. Situation R, the guests arrive. There's an M situation where presents are given, an A situation where we're taking out the trash, and a Q situation where there's going to be eating of ice cream and pie, right? So don't know where we're at. I guess cake is not the standard here today. But in either case, the robot has these 5 tasks, and the scenario is a birthday party. When does the robot light the candles? Okay, is it before or after they sing Happy Birthday? Is it before the guests arrive? Clearly, hopefully the robot doesn't light the candles after situation Q, right, where the candles have just been blown out and applause has happened, and at that point the robot lights the candles perhaps again, right? The candles, that's something that we want to have happen once. When does the robot scan the presents for weapons and explosives? Prior to giving the gifts, hopefully. We don't want the robot doing a scan after the gifts, right? And there's one of the robot's tasks is to greet and scan the guests. Maybe it's a pat down. Is he scanning them for guns? I don't know. This is a strange kind of party here. Don't know who's invited or what the terms are. But we have a scenario, and we have situations within that scenario, and things have to happen in sequence. Okay, so from the robot's perspective, what does any of this look like? What does it mean to light candles? What are candles? Robots have no idea what candles are. They also have no idea what guests are. What does it mean to scan the presents for weapons and explosives, right? Robots don't come with de facto knowledge about weapons and explosives, right? Or even de facto knowledge about taking it out the trash. In fact, the robot doesn't know how to do any of these things just out of the box, so to speak. It's has some number of microprocessors, microcontrollers. It has some number of actuators, end effectors, and it has sensors, and it's going to process any signal or set of signals through those components. And things like candles and birthdays and birthday parties and explosives and taking out the trash, none of those things have any meaning beyond how they register with some actuator, how they register with some sensor, how an end effector is going to interact with it in some kind of way. That's what the robot has to work with, right? But as users of robots, we want the robot to accomplish some set of tasks within some scenario situation that has meaning and semantics to us. And so we have to, as robot programmers or roboticists or ontology engineers or knowledge engineers or robot enthusiasts, we have to have some kind of way of taking and representing or communicating the scenario and the scenario task, to the situation task. We have to have some kind of way of communicating that to the robot, right? But we need to know how the robot is going to be, and I don't want to use the word perceiving here, but I do want to use the word interfacing. But perceiving, you'll see that a lot of times in agent references where we'll talk about agent perception. Here I'm just going to talk about, I'll use the term interaction, right? And so I noticed I said that the raw view is like a superset. I'm dividing that raw view into what I'm calling the sensor set and the object interaction. So like in this situation, all our robot has is a camera, a spectrometer, LiDAR, a magnetic sensor. It has electroconductivity, an EC sensor. It has a compass, GPS, and gyro. It has a sampler and ultrasonic sensor. And that's the point here. The robot needs to interact with the birthday party and all of its situations and its moments and its events through this set of sensors. I don't see anything in this set of sensors that says birthday cake or guests or or candles. So somehow, with the LiDAR, with the spectrometer, with the electroconductivity, with the camera, somehow we need to represent what a birthday cake is, what a candle is, what a guest is. The notion of when to blow out the candles. We've got to represent that using one of these, 7, 8 sensors that we have. Also, the robot's ability to interact, exactly how is it going to blow out those candles, right? Is somewhere in the actuator, with its actuators, right, is how it actually does some of the work, right? Tractor wheels for mobility, wheels, legs, pneumatic hover capabilities, maybe it's end effectors, some kind of way it has tools or claws, or maybe there's a duster on the end of those, like the end effectors, like the kind of where you blow out the canned air, where you blow out the dust from like a device, some electronic device. The robot may have those for end effectors, or maybe that's what he's going to use to blow out the candles. The manipulators, any kind of robot arms that we're talking about, pulleys, those kind of things. So you have a couple sets of, you have the actuators that the robot has, and then you have the sensors that the robot has. It's got to interact. If we're talking about the robot's perspective of the birthday party, the robot has to interact with those components of the birthday party through this limited set, through the object interaction set of actuators and through the sensor set. And so it is up to the programmers, the robot programmers, or the roboticists, or the robot engineers, or the ontologists, ontology engineers. It's up to those folks to take a look at this sensor set and this object interaction set, this actuator set, and figure out, how do you get birthday cake out of this? How do you get birthday candles? Maybe with the camera, I can show store with the robot what a birthday candle looks like. But as we all know, for those of you that, and especially if you have an international experience, birthday candles come in many shapes and forms. So you're going to have a lot of pictures of birthday candles. Also, maybe we might use a spectrometer to identify whether the substance we're looking at is wax or not, or maybe there's some other kind of butane container that's actually playing the function of candles, right? We might use LiDAR that helps us determine where the cake is. We've been told that the cake is in the center of the table. And maybe LiDAR plus the camera plus the spectrometer will let us know where the cake is, right? And then maybe we can get our end effector that blows air to blow out the candles that way. And so if you get the point here, this is what the robot is working with. This sensor set and this actuator set. It doesn't have anything more than this for the most part. We'll get into the law of view a little, and it can bring the law of view to bear a little bit on this. But if we're being honest and we're trying to design this robot application properly, then you have to be able to describe the scenario, in this case the birthday scenario, and all the situations in the scenario, at least the ones that the robot has to interact with. And the robot task, you've got to be able to describe those things relative to this sensor set and this actuator set. And this is the challenge. And this is one of the fundamental things that we have to do as robot programmers, right? How do we represent reality? What's the representation? We have cakes, we have candles, we're scanning for weapons, all right? We have guests. How do I tell the guest apart from the cake and apart from the trash that needs to be taken out? How do I make that difference clear to the robot if all the robot has is this set of sensors and this set of actuators? Okay, and so notice here, I've got our birthday party scenario, and the birthday party scenario goes through the raw view and the saw view, and it ends up at robot control. And so if you literally look at that raw view and the saw view as the prism, as the glasses through which the robot interacts with reality, then I think you'll have the right paradigm, right, for programming. You can't think of the concept of a birthday cake as we think of it in our normal human experience, regardless of what country we come from. There's normally some kind of celebration of what amount, of the birthday. We can't think of it in those kind of cultural, social terms, even though we want the robot to interact in those terms, and in that cultural context. The robot doesn't. That cultural context is not available to the robot. It's not a part of the robot's actuator set, and it's not a part of the robot's sensor set. Now, it can be a part of the robot's law view, but that's we'll talk a little bit about that later on. But for now, we want to just say, okay, here's the mission, which is impossible. The mission is to understand the syntax, the semantics, and of the context and the robot's environment, understand the what it's dealing with at the cultural and social level, and then find a way to represent that reality in terms of this sensor set and this object interaction. And that's what programming and robot design and robot engineering, that's what it's all about. That translation from human experience to machine capability, right? That's the thing. That's the thing we've been toiling with all week long, this week in Robot Week. And in fact, the Rome people and H2O people at CTEST, that's all we do. Okay. Now, like I said, that raw saw and law view, those representations, they don't just come out of nowhere, right? Those tend to be produced by roboticists, robot programmers, robot engineers, ontology engineers, and knowledge engineers. In many instances, folks with those kind of functions or titles or unofficially this functioning in that capacity, those are the folks who are tasked with translating a situation or a scenario from human terms to machine terms, right? Our UltraSpark processors, our ARM processors, our Ryzens, our Intel processors, those things have an instruction set, and that's all they understand, right? They don't know anything about birthday parties and birthday cakes. That's not a part of the vocabulary. They don't know anything about guests, right? They know about adding something to the to the SP register or the AX or the DX register or something. They understand very low level hardware type instructions. And this list of folks and folks that operate in this capacity are responsible for converting things like birthday party into sets of instructions and discrete structures that a machine, a robot, an automatic computer scenario can handle, right? And so what they tend to produce are logic designs and algorithms, data structures, discrete structures, functions, ontologies, and many, many, many mathematical models. If you think robot programming is something else, it's not. And I hate to rain on anyone's parade, and folks that have some other paradigm for what's going on. At the end of the day, we are talking a system of microcontrollers, microprocessors, sensors, actuators, and end effectors. And in order for those things to function in some cultural context, interacting with human beings or animals or whatever, we're talking about algorithms and data structures and discrete structures and mathematical models that represent reality. And those things don't come easy. All these artifacts are produced, and when they're produced, they require insight, imagination, creativity, experience, knowledge. I'm going to have luck here. It's a lot of talent involved. There's no shortcut to this. At least we haven't found one to get robots to do real things in real context, in real object interaction, in a safe, effective method. There's no shortcut, and it requires talented people to be involved and that are creative, that have the requisite knowledge and imagination, right? And so I have a list here. It's by no means is it restricted to this list, but these are kind of representative, right? Ontology engineers, knowledge engineers, robot programmers, roboticists. Okay, you need some electrical folks in here. You need some system software. Lots of people are necessary, but these 5 here it's a good start to give you some idea of what we were dealing with this past week, and like I said, and what we deal with all year. And so, I bring this up, and I know we discuss this every year at Robot Week. We're building an ongoing tool that we call ROSE. It's a robot scenario and situation editor. And the whole purpose of this piece of software is to capture the scenario and the situation in terms that the robot can deal with. Okay? Not in terms that the people think in, although some people do think in these terms. Some people do think like robots. Sadly, I think I'm in that group. But in either case, the point of this software is to give the programmers, the designers, and the developers a tool that lets them capture the scenario and situation in terms that the robot can understand. Actually, this is a work in progress. It's an internal tool that we have here at CTEST Labs, and we throw up some screens here, and names have been changed to protect the innocent, right? But enough of this is here for you to get the idea of what's going on with this software. We do direct programming, where we are directly sending instructions, particular movements to servos, or particular rotations, distances, and those kind of things. Then we have a task level where we are describing the task to the robot that we want done. And then at the storage programming, that's the level where we try to describe the scenario and the situation, right? We cannot go through all of this software here. We need to have an entire talk or two just describing the task programming option and the storage programming option. But we just want to show you, here's the beginning for what our participants used this week. We have a profile here where we create the robot profile, one of the robot profile, and we capture the attributes. We find out what microprocessors and microcontrollers are involved. We get what all of the sensors are, how many robot arms are involved, the travel mechanisms. Does the robot roll around? Does it have a tractor type scenario? Is it a hover robot? Is it a aerial robot? Is it bipedal? Those kinds of things. And so here we're really capturing the actual profile of the robot, which becomes important physically. We also have a part of this where we start to talk about the environment, right? Like the objects that are in the environment. Notice here that we have the ability to load previous situations, which is an interesting feature once you folks realize. We ran into some of that this week. Is the robot facing this situation for the first time? Or is this a situation that the robot has faced in the past? If it faced the situation in the past, well, was that interaction successful completely or in part, or did it fail completely or in part? Bringing into giving a robot a past situation, a past scenario, an ability to compare and contrast is a special kind of programming. We did a little bit of that this week. We defined the robot areas and robot objects and those kinds of things. Like I said, this software, we could spend many, many, many hours talking about its features. But this is an entry point for those that are programming to start to communicate with the robot what that scenario, that situation, and that environment is, and what it's going to look like. For instance, here's a screen where we really talk about the objects, right? Let's say, for the sake of argument, the thing that we're describing is the birthday cake, right? I might be able to say where the birthday cake is located with the location here. I might be able to give the mass of the birthday cake. I might be able to communicate to the robot the colors of the birthday cake. maybe the volume, what material the birthday cake is made out of. And then, like I said, for geometries, I want to give the robot some sense, of the geometry that's involved. Is the birthday cake a cube, or is it more like a cylinder? Is it more like a torus, or is it really shapeless, right? And if it's shapeless, what do we do with the robot under the object under those circumstances? So part of communicating the scenario and the situation to the robot is specifying these attributes and these objects and giving those things identifiers. And of course, there are many approaches to having a robot, kind of map out of the environment, right? You send the robot out with a LiDAR and some kind of image recognition, and you want it to map and scope its own environment out. Yeah, in a fantasy kind of way, that works. But in reality, that's only going to be one method, right? We're only going to let the robot automatically map the objects in the environment. That's only one step, because that mapping process involves error, right? The robot's going to get some things wrong. And so we have this step as a second safety check, so to speak, or reality check. So so we define what's actually in the environment, and the geometries and the state of the matter and all of those kind of things, the state of the energy. We define that, and in addition to us defining that manually, the robot automatically gets what it can get. And so what you end up with is what the robot sees and what the robot expects to see based off of what we've programmed. Okay, so there's an expected reality, and then there's a reality that the robot actually maps, and then there's a reality that's comes from the law view, that is a reality that's based off of what should be the case. We have what the robot expects, we have what the robot actually measures, and then we have what should be the case based off of a priori and other posteriori experience the robot has. Like it says, we have the ability to go in and retrieve situations, right, from the past, and retrieve scenarios from the past, and success and failure from the past. And so from that extent, the robot has posteriori knowledge of certain object interaction. And then there's a priori knowledge that's built into its programming, and expectations. And then there is what the robot's able to measure. You send a robot into an environment to map the environment and to try to do object recognitions and those kinds of things in real time. But that's only going to provide you a part of the picture. If you're doing this for real and not for play, you'll find out that mapping stuff only gets you so far, right? And there's going to be some explicit manual programming by ontology engineers and knowledge engineers and roboticists and robot engineers. That's just the facts. Okay? And then, our robot has tasks. And in our situation, the stuff we dealt with this week, like I said, some of these names have been changed to protect the innocent. But we can talk about these 5 concepts that robot wanted the task. Wanted the robot to determine something, sometime to retrieve something, sometime to go somewhere, sometime to put something somewhere, sometimes to locate things, right? And so there's sets of tasks going on. Like for instance, the ability to take out the trash in the birthday party scenario would involve the task of retrieving the trash and then traveling somewhere, and then putting that trash somewhere, right? So, and maybe even locating. Actually, probably now that I think of it, we probably had all 5 of these actions, because the robot has to determine what's trash and what's not, right? So there's some determining functions here. Like I said, all of these are just dialogues that we drill down into complex pages that I did not want to show in this brief talk here. I just wanted you to have some sense of the audience to have some sense of the tool or in the process and the challenges that the participants had to deal with this week, and how we went about it in part, right? So these 5 tasks could be done by themselves or in combinations, or in many combinations and in different orders. The robot is actually making plans to decide when and where and how much of these tasks to actually do. But Rose was programming Rose. You were able to say what some of these tasks were. Okay, and then when the robot is done, let's say for its birthday party processing, it gives a what we call a situation report on every object that was in the scenario or in the situation. So every object that was there and its status, what its beginning status was. We find out what its end status was. Like the candles, at some point were not blown out. They had to be lit, and at some point they were blown out. At some point, the guests were not present, and then at some point, the guests were present. So the statuses of everything that was involved and the changes and transitions they made during the course of the scenario or situation, the robot reports. We get a log report here. We get a object status report. The robot lets us know which actions were successful, which were completely successful and which were only in part successful, which things failed in a spectacular way and which things failed in not necessarily a spectacular fashion, but did fail. Okay, so this situation and scenario report, it's human readable, but the robot also has it in a form that it can work with for next time, right? Again, we talked a little bit about this, and we drill deeper into this every robot week. This is just for our audience to have some notion that there is a status report that the robot gives. Any assertions that the robot has, new assertions that the robot has had to make, or assertions that it's used, it's going to list those. It explains its assertions and its actions. If there are questions for the programmer that the robot has at the end of a project or scenario, it will actually post those queries so that the end user, roboticist or intelligent engineer can respond at some later time. And the point that I'm making here is that all of these things are all meant to deal with everything from the robot's perspective. Instead of the perspective from human beings, which we are a function of so many years of evolution, our DNA, our cultural and social experiences, our biology, and the things that we do, and the way we interact with reality is a function of all of that. Our robots are a subset of what we are. It's a subset of our experiences, our technologies, our capabilities, and it does not have the complete human experience. It's really a very small subset. So when we program robots, what we want to say today is that it's a good idea to start with the robot domain environment. It's a good idea to look at what the sensor set of the robot is and what the actuator set of what the robot has, and your ability to program the robot successfully and have a successful application will rely on the ability to convert that scenario and situation into things that can be found in the sensor set and the actuator set. That's pretty much it. And if you can't do that, you're not going to have a successful robot application. There's no way to do it. You need representation. You need to represent whatever real situation and scenario is in, the robot is in. You need to be able to represent that situation and that scenario in terms of that sensor set and that actuator set. And if you can't do that, stop. In the flowchart, back in the flowchart days, there was a stop symbol. If you get here, just stop. Don't go any further. If you don't have a model, if you can't express the situation and the scenario in terms that the robot can understand, using languages like C and C++, Assembler, Java, I don't know, maybe Python, whatever, answer set. Maybe we're programming in Klingo. If you're doing that kind of program, we use a lot at CTEST Labs. We use a lot of Prolog and C++ and Klingo in our programming. And if we aren't able to express the situation and scenario in terms of those languages, if we can't get it that far, we stop at that point. If we can't figure out mathematical models for it, we stop. Right? So many times, even before we get to the actual implementation model, we have to have a mathematical description for the scenario and situation. And if you can't describe the scenario, the situation, the events and the moments, if you have no mathematical language for that, you probably won't have a successful project, right? So that's what I wanted to leave you all with, for the most part, is we're at the end here, and so maybe we should, and when you're talking about the end, we should end with the beginning. And the beginning of robot programming, real robot programming, is really being able to translate that environment, to represent that context, that situation, and that scenario in terms of sensors, actuators, end effectors, algorithms, discrete structures, right? Functions, data structures, be able to represent that scenario and situation as those things at the very beginning. If you can't, you're going to get in trouble. And this idea of having the robot learn it all on its own some kind of way, that's fool's gold and a fool's errand. And so we learned that a lot this week. And so the participants got a chance to see that up close. So that was pretty good. I mentioned that I was going to say something about the law view before we brought this to a close. The raw view includes this, but we focused on the sensor accessible world. That's how the robot interacts with the situation or scenario through its sensor set. Right? And then you had an actuator set, the arms, the wheels, the legs, the end effectors, right? How it interacts with the world there. The law view, which is the logical view of the in the environment, the context, the situation, the scenario. We have that logic view is two big components for us, is a priori knowledge representation and a posteriori knowledge representation. And I'm leaving it at that here now, because when we go offline, this is what we're going to be talking about for the folks that are they're in our special group, that are special patrons. We will go a little bit further into the law view, and we've got another 2 weeks here that we're going to be doing things. And then probably for next year's Robot Week, we will probably start with the law view. We spent so much time this year on the saw view and the raw view. So I think it's going to make sense for us to get into the law view. And for those of you all that are listening to this live, we're going to when we go offline, this is going to be the conversation. But it's these three views, and it's dealing with the scenario and the situations, the events within the situations, and the moments within the events from these three views. That's what robot programming is all about. We found that out this week, the easy way and the hard way, right? And we had a lot of fun, and it's been real, and we look forward to seeing you guys, and thank you all for checking us out. And if you're online and you weren't, if you're going to see this at a later time, thank you guys for watching, and remember to check us out. And some of the work we do is on our RUR site. You can check out some of the stuff we're doing at CTESTlabs.org. You can come see us at the Oak Hill Robotics Collaborative Makerspace. And so we'll see you guys next year. Thank you.